Hi, welcome to another edition of Linear Algebra. Today we are going to extend our set of applications to another item, and the item for today is going to be network analysis. Let's go take a quick look at this. So we said we have a set of items to talk about with respect to applications of linear systems. We talked about resource allocation and balancing of chemical equations. Today we are going to go to item 3, network analysis, and the main example of that is going to be traffic analysis. So let's go ahead take a look at this topic. So we are going to talk about network analysis. So let's draw a basic example to see what we are talking about. We are essentially talking about traffic flows. So in this section you are going to see essentially something looking like a simplified city map. So is it going to be a map? So here we see some points that we probably on a map we are going to call them intersections, but they could be given some generic name in these applications. So A, B, C, D, which you would have called intersection in our everyday language, would be called something like a node or a vertex. And then we have a set of roads. These roads they might be called, well, we might as well call them roads, but also sometimes referred to as branches or arcs or similar language. So then we go ahead and measure the traffic flow in each of these roads. So here suppose we have measured the traffic here in certain number of units, and it comes out to be, say, 5 units of vehicles per unit of time. So we indicate how heavy the traffic is in some unit here, and we indicate a direction for the traffic flow. So here is another traffic flow here. Perhaps on the outlying roads we specify what the flow is, and here I'm writing some numbers. In this one traffic is heavier, here's 20, and say the traffic here is, say, 30. So the question is, if I know if I measure these traffic levels at these locations, can I figure out how it's going to be in the interior of this region of the city? So suppose we designate traffic flow here to be, say, flow 1, and here is, say, flow number 2, and say here we have flow number 3, and here is flow number 4. Our assumption would be that these are one directional flows, or one-way streets if you wish. So when we specify the flow direction, that is how the flow is supposed to happen. We are not allowing the opposite flow in the opposite direction. Of course you could have assumed that as well, but here the assumption in the textbook is that these flows are all positive numbers, and that would be a restriction that we are going to follow. A negative number would have meant going in the opposite direction. Okay, So we have the concept of a flow in each of these branches or roads. By the way, another terminology that they might use here, sometimes they might refer to it as a junction, which is also similar to everyday language. So what is the basic idea? Basic idea is that at any of these intersections, the incoming has to be equal to the outgoing. So the general idea is that if you have a road and say we have a fork in that road, and the flow coming in is say F1 and the flow going out is well, we have two branches going out and say one branch coming in, our conservation would mean that the incoming is equal to the outgoing. So sum of the incoming is equal to the sum of the outgoing for the current, and that is referred to as a conservation of the quantity under the consideration. So for example, we say if these are cars coming to intersection, well, the number of cars coming in should be equal to the number of cars going out. Otherwise, either they are disappearing at the intersection or they are being born at the intersection, and conservation means our material are neither being destroyed nor is being created. Okay, so this gives us our conservation law, which is going to give us one equation per each of these nodes. At each node we can write incoming is equal to outgoing, and that's going to be a set of equations. So for example, at node A we have the incoming, which is like 5 plus 10, and outgoing is F1 plus F4. Well, how about node B? At node B I can identify F1 as incoming and 10 plus F2 as outgoing. At node C, my equation is going to read my incomings are 2, 3, and 5. So 5 plus F2 plus F3 is equal to outgoing, which is 30. And at node D, we have one more equation, which is incoming here is 20 plus F4, and the outgoing is F3. Now, if you look at these equations, first of all, well, we see that we have a linear system. That's why the topic shows up here. As a matter of consideration, let's just talk about the situation here. This is of course a simplified problem where all the numbers are steady state numbers. So we are not looking at any kind of a traffic jams or pile-ups and such. This is like a steady stream of say cars or people coming in and then going out and such. So that's restriction number one. This is a steady state picture. Restriction number two is that, well, from the context we have to know if our directions are essentially chiseled in stone or not, meaning are these things one-way streets or is it possible for us to allow flow in the opposite direction? As we said, most of the textbook problems, the direction is to be obeyed, and like that means all the traffic here has to be from A to B, and that means the F1 has to be a positive number. Item number 3 that we can pay attention to here, if you look at say this is the center of town and these are coming from outside or leaving the town. If you are looking at the incoming to the center, you have 5 and 10 and 20. So let me write down all the incoming: 5 and 10 and 20, and then we have another 5 coming in, and the outgoing will be this 10 and 30 that is leaving town. So if you look at this thing, you see there are 40 units coming in and 40 units going out, and this is of course means whatever is coming in is leaving, and again, that means a steady state. We don't have a pileup of the items or cars or people in a certain location. So it's a steady state picture. Another view of this thing, when you write so this was our incoming and these were the outgoing at each of these nodes. If you add them all up, 5, 10, 5 and 20 are just these numbers, so it becomes 40, and F1, F2, F3, F4 on the other side. 10 and 30 is also 40, and then we have F1, F2, F3, F4. Of course, what this thing means is that of these 4 equations, one of them is going to be considered redundant. Why? Because, well, this is always true. Something is equal to itself, it's always true. If you take this and subtract the sum of the 3 equations out of that, you'll get the 4th equation. So what that means is that one of the node equations is going to be redundant. In this type of analysis, when we write all the equations with all the nodes, we have one extra equation that if you write it, it doesn't hurt. If you eliminate it, it does not hurt either. So one way or another, you are going to handle that situation. So it might be safer just to write all of them and notice what happens. So I go ahead now, write this thing in a standard notation that we have. F1 plus, well, F2 and F3 and F4, let's write it in the standard format, is 15. Second equation reads F1 minus F2 is equal to 10. Third equation reads F2 plus F3 is equal to, I take the 5 to the other side, becomes 25. And if you wish to write this one, perhaps we can write it as F3 minus F4. So I take the F4 to this side and leave the 20 out there. You can write it in a number of ways. So this is the standard format of those equations. And again, you can do Gauss elimination or Gauss-Jordan elimination to this, so I'm going to do another practice of that software we talked about several times. Let's see what happens when we so I double check my equation to make sure I have done everything correctly. F1 and F4, that is equal to 15. F1 minus F2, F1 minus F2 is going to be 10, and F2 plus F3 is going to be 25, and F3 minus F4 became equal to 20. Okay, this is simple enough for us to do by hand, of course, but let me leave that to you. And sorry. So we had that let's go edit this thing. I have 4 equation, and then therefore it has to be 5 columns. Is that right? Then my here was 1, and then this is 1, and this is 15, and this was 1, and then minus 1, and this was 10, and this was 1, and the 1, and 25, and this is 1 minus 1, and this was 20. Okay, we entered, so we say resume to go back to the Gauss-Jordan steps. Pivot, target, so everything else of course is 0. I go here and standardize this thing. This divide by the leading element and makes it 1. It's kind of easier to look at. Then 1, eliminate the one below, and then this is 1. I eliminate the number below, and what I get, the last equation, is across the board 0. So that means what we mentioned before, that one of our equations is redundant, so it drops out. If the right hand side was non-zero, indicates in our problem that our assumption is not holding, something is not quite right, there is no solution, or the problem is not static. So in this case, fortunately we don't have any of that problem. We see that we have pivots here in these 3 locations, and this is going to be what? This is going to be indication of our parameter. So let me write this equation as I have it here, f2, and so this one was traffic number 4. This is f4. So I write all of these numbers. Last equation, there's nothing useful to write from there, so we go back to our paper, we copy this system over there. Okay, so we did the simplification. The first equation stays exactly as it is. You say f1 plus, making space for the missing variables, so I put a dot there. The second equation became f2 plus f4 is equal to 5. The third equation was f3 minus f4 is equal to 20. Is that right? Then what? Well, we are going to the variable that's not associated with the leading entry, that's going to be declared as a free variable. So all of this as a free variable goes to the right hand side. I might as well take f4 to be our parameter, call it t, then f3, f4 goes to the other side, becomes 20 plus t, f2 becomes 5 minus t, f1 becomes 15 minus t again. So these are our solutions. Now we come to our discussion about what we assumed about these, the application we have in mind. The application we have in mind, we said these are the arrows indicate one-way traffic flows, and as such the traffic has to be positive. We are not allowing anything to go backward. That would have been considered negative if we were allowing it, but we are not allowing it. In that case, subject to that assumption, f1, f2, f3, f4 has to be non-negative, cannot be a negative number. So what does that mean? It means we have 4 inequalities to solve. These are to be all satisfied, and then we go and find out what that means. So the first one simply says t has to be positive. Second one says t has to be larger than minus 20. Of course, between these two, the trump is with the first one. If t is positive, it definitely is also bigger than minus 20. So this equation reads that t has to be less than 5. So I write t less than or equal to 5 here. And the first one, it says that t has to be less than or equal to 15. So we look at all of the restrictions that we have here and says, okay, what is the what's the restriction? What's a restriction that makes all of these things to be true? Okay, we have to take essentially the intersection of all possible range of t values. So of course, If t is larger than 0, this one will be true, and if it is less than 15, then that one will be true as well. So when we summarize this, we come down to the fact that t has to be between 0 and 5, and then all the conditions will be simultaneously satisfied. So we consider this, and then of course if t happens to be a whole number, meaning if it is number of people, number of cars and such, and then it has to be either 0, 1, 2, 3, or 4, 5. If the flow is with respect to a continuous quantity like a flow of water and material like that, well, a fractional value would make sense as well. It all depends in the wording of the problem, what is it that you're measuring by these flows. Okay, once you have t between 0 and 5, then you can go ahead and declare what's the restriction with respect to any of these 4 flows. So if t is between 0 and 5, then f1 is at most, when t is the smallest value it can have, f1 will be having the largest value it can have. So largest value of f1 is 15. If t extends to 5, then f1 falls down to 10. So maximum minimum of f1 is this. Same way you can figure out for f2. So if t goes to 0, this is 5, and at the lowest value it becomes 0. And then f3, at the highest value it's 25, at the lowest value it is 20, and f4 is just same as t. The highest value of this thing is 5 and the lowest value is 0. Okay, so maximum minimum of each of these flows. Now just to be clear, we are not saying that all of these things are going to happen simultaneously. Now individually, if you look at this flow, the lowest you can have is 20, the highest you can have is 25, and so on and so forth, not implying that the maximum or minimum values, all of them occur all at the same time. That typically does not happen that way. Okay, the problems in this section are all similar to this, except of course this is a very simple network. It's like having a small city with just 4 traffic lights on it, and that's not common. So in general the maps are much bigger, so your system of equation is going to be a bit bigger than just 4 by 4, but given that you have that little software, it should be easy for you to analyze this type of problems quickly and without much difficulty. Okay, our next topic is going to build on this thing, but it's going to go much further in complication. We are going to talk about electrical networks in the next lecture. Until that time,